Okay, so we're going to continue looking at a little bit of information on power, and we're going to tie it together with a couple of other things that we can calculate. Now, these are less likely to show up on the AP exam, but they are things that could be useful to be familiar with and answer some day-to-day type questions. That being said, I could also see a question like this coming up, depending on which exam you're taking, so we're going to go ahead and cover it, though this will probably not be as long of a video. So what we're going to look at is, one of the things that we talked about in class was the following. So we talked about different potential differences. And so of the things that I ended up asking were things like, well, different types of batteries. For example, here, this one is one that you all are hopefully familiar with. It is a 9-volt battery, named because its potential difference is, wait for it, 9 volts. Or at least that's what it should be on a regular basis. That's normally what they're spec'd at. Now, one of the things that we got to talk about is in real life, things are not necessarily made to be perfect. We saw that with our resistors. So for instance, if I set this to volts, my voltmeter here, the small side is the positive and the large side is the negative. I can actually put this out there. I'll measure this, and these batteries, this battery is coming up as 8.91 volts. So pretty close to the 9 volts it's supposed to be. I have been using these, and as you use them, they can actually change their values. Let's compare that to a different one. Ooh, this one's at 9.17 volts. So something to keep in mind. All right. These are 9 volts. Then we went through and we talked about other types of batteries. So let's talk about a few of them. Well, some of the ones that we've seen here are AA's. Those are pretty common ones. So I'm going to put a AA here. I'm going to put a AAA above it, kind of going in the size of them as they get bigger and bigger. I don't have all of my examples here, but there's a C-cell battery, there's a D-cell battery, there are lantern batteries, and so forth. So let's talk about a AAA. A AAA has a potential difference of 1.5 volts. And then a AA, in fact, let me grab one of those real quick. I think I could have come better prepared, but to be certain I've got some AAAs here, which is good. Hey, look at that. And I have a C-cell. Okay, so I'm not poorly prepared as I thought. Sorry about that. Let's go ahead and check some of these. So it's supposed to be 1.5 volts. On these, the little bump end, the side that has the bump, is the positive, and the other side is the negative. So if I take this and I put my negative side on here, let me see if I can put the meter in range here. Let's see what we end up with. I end up with 1.61 volts. So this one's a fresh battery and a little above the 1.5 that they're spec'd at. So this is 1.5 volts. In fact, if I look on here, it probably says that somewhere. Yep, AAA 1.5 volts. If I check a AA, now these have been used a little bit, but let's see what they come up with. Negative here, positive over here. 1.59 volts. These are also spec'd at 1.5 volts. Now, I usually go through and ask my students as we start going through this, start off with the AAAs, point out that they're 1.5, and I ask what the AA is, and they usually guess something like 3 volts. They're a little surprised when that one's also 1.5 volts. So let's take a look at a C-cell battery. So I'm going to put the negative here and then the positive over here. And we're going to find that, hey, look at that. Hopefully to no one's great surprise, 1.58 volts. These are also spec'd at 1.5 volts. And when you check a D-cell battery, it's also 1.5 volts. And at this point, you may be thinking what most of my students think, which is, wait, why are there different sizes of batteries? Well, we're going to get to that. First off, let's go ahead and fill in a few others that we could talk about. There's a lantern battery. Pardon me. They're larger and more rectangular. They're used for, among other things, I know some camping applications. They have a potential difference of 6 volts. They're a bit different. It's not that everything is 1.5 volts. We've also got car batteries. Car batteries can actually fluctuate, depends on what type they are, but a lot of times a good estimate is 12 volts. Same thing for motorcycle batteries and things like lawnmower batteries, that sort of thing. All right, there are a couple of others that I do want to bring up while we're taking a look at them. I collected some information for this. So for instance, I was looking at some of the iPhone batteries, the batteries that go into iPhones. Let's see, iPhone fruit battery is... I found some stuff online. It was hard for me to get their full technical specs because that's usually how Apple rolls. But from what I found from some of the pictures online, the iPhone 5 had a potential difference of 3.7 volts. The iPhone 6 was 3.8 volts, at least from the images that I found online that I could read off of their batteries. Now, I don't personally have a fruit phone, so I didn't feel like taking it apart and finding out. I actually meant to check my phone's battery before I started recording, but this is plenty enough for us to look at. The iPhone 6 is a 3.8 volt. I'd imagine most of the phones, usually they're somewhere around 4 volts, somewhere in between 3 and 4 volts is the standard supply on that. Now, let's go back to this. Let's talk about what's going on with these batteries. Why have a AAA or a AA or a C or a D if they all have the same potential difference? Aren't they all the same? Well, they're not. And so here's the thing that we need to talk about that ties back into what we said before. A potential difference only describes relative heights. We don't know how much energy is there until we know about the object. So for instance, I could tell you that I've got something above your head, maybe 2 meters up in the air, and it's hanging over your head. How worried should you be? Well, I have no idea. What do you have above my head? Is it a bowling ball? Then I'm worried. Is it a tissue? Not so worried. And this is the thing. You may have heard me say in class that voltage, potential differences, by themselves are not dangerous. It's actually the current that you should really be worried about. A lot of times, though, high voltage comes along with high current, so we should be very careful with that. I'm not telling you to ignore high voltage. But even if you have something that's, say, 10,000 volts, my Van de Graaff generator, the thing that I put my hands on and my hair stands up, that gets up to several 100,000 volts. That's kind of like dropping something, since we're talking, I mentioned that potential differences are like heights. That generator is kind of like dropping something off of a skyscraper down to the ground below. Now that sounds like it's going to be pretty dangerous, but what if I drop a tissue from the top of a skyscraper down onto your head? You're probably not going to be that worried about it. Now, if I drop a bowling ball, that's a big difference. So one of the things you've got to understand, while all of these in particular, the main ones we use, they have the same potential difference, the same voltage, they are not all the same battery, and that explains why we use different batteries at different applications. There's another thing that we can talk about. It's called capacity, is usually what it's referred to for the batteries, the battery capacity. This describes how big of a height the objects are falling through, and that gives us some energy, but we don't know what the energy is until we know the charges that are moving through it. Well, there's a big difference between this battery and this battery. You'll notice in size. Well, part of the reason that they're doing that is while their potential differences are the same, they drop from effectively the same height, they push with the same amount in a circuit. The biggest difference is in their battery capacity. This will run out much sooner than this, and they both will run out much sooner than this. So when you see a lot of bigger objects that require more energy, you're going to start moving more towards, say, a C-size battery or a D-size battery. If you've got something that requires very little energy, like remote controls, many times they operate off of a AAA, not a whole lot of capacity. So let's talk about the capacity and what we can learn from that. I collected some numbers on this. Let me see if I can get these right. Now, capacity is many times kept track of in something called milliamp hours. Now, I'm going to bring something up here. Let's remember our units, because units are a great way to keep track of this. I told you that an amp is equal to a coulomb per second. In other words, it's charge divided by time. And just like we saw with the earlier parts of power, I can now multiply that by an hour, which is a unit of time. So while this is a strange unit, milliamp hour, what it is best describing is a charge. Now, this relates to not the total charge in a battery, because it turns out they're electrically neutral, but the idea that you could get from this is how much charge, on average, this battery could move, and as a result, gives us an idea of how much is stored in the battery and what it can do. So, milliamp hours. Now, in this case, an amp is a coulomb per second, so a milliamp would be 1/1000th of that. But this is the standard thing that you're actually finding these in. So for instance, a 9 volt for an alkaline one, at least the data that I've got says that it is 0.6. In fact, this is not a potential difference. It's also not a current, so I'm not going to mark it in blue. I'm just going to switch over to black. All right, is 0.6 600, sorry, gotta remember where my notes are, 600 milliamp hours. For the AAA, for instance, let's see, where are my notes? 1,200 milliamp hours. Now, these are rough values, depends on what brand you've got and a couple of other things, but this is a pretty good representation for most of them. AA's are 2,700 milliamp hours. They have the same potential difference, but they have different capacities. Effectively, a way you could look at it, a different quantity of charge that they can move. And remember, we don't end up with the energy until we take the potential difference times a charge. Volts are a joule per coulomb. When we multiply those by the charge that is there, the mass that is there for the gravitational equivalent, that's when we can find out the total energy. So the C-size battery, where did I write that down? 8,000 milliamp hours. D-size, 12,000 milliamp hours. Let's see, for the lantern battery, did I actually write that one down? I don't think I got a capacity on that one. I feel kind of bad. We'll skip over that. We've got plenty to take a look at. The car battery, while it's only 12 volts, now this is one of the things that we brought up where students said, well, could I replace my car battery with two 9 volts? I wouldn't recommend it, and here's why. They've got, for the car battery, on average, or I should say, I think this is actually for a large car battery, but still gives you a good idea, 50,000 milliamp hours. Again, don't get caught up in the potential difference. While it's an important part for our circuit, the batteries are also affected by their capacity. And we're going to see how that ties into energy and power. The iPhone, let's see. Let's go with the iPhone 6. The reason I say that is I managed to get more information on that one. On the iPhone 6, that's 3.8 volts, and the image that I found said that we had 1,810 milliamp hours. Now, the iPhone 10, the latest one, I couldn't find the potential difference on it, so that's why we're not looking at it, but it boasts a battery capacity of 2,716 milliamp hours, a noticeable amount more in its capacity. So that's one of the things that they're promoting for that one. Okay, I'm going to set this stuff aside, and let's play around with this and see what we can find out. First and foremost, a great way to understand these values is basically to say the following. For this 9 volt, it can supply 600 milliamp hours, which means if you are pulling 600 milliamps from it, a current, it will last for 1 hour. Or if you're pulling 1,200 milliamps, it will last for half an hour. If you're pulling 300 milliamps, it will last for 2 hours. Or if you're pulling 1 milliamp, it will last for 600 hours. You can work with this milliamp times hour, where the two of them together, whatever current you're drawing, times however many hours you get, will come up to the pretty much total capacity there. So, for instance, and this is one of the things that I wanted to talk about briefly here, you can also find out how much charge is coming out of your battery going into something by saying, okay, let's say that my current is 600 milliamp. All right, that's the same thing as 0.6 amp, which is equal to 0.6 coulombs per second. If I want to know how much charge is going by out of that battery, for instance, or through my circuit in 10 seconds, then I can take this. This is 0.6 coulombs per second, 600 milliamp, and I multiply that by, say, 10 seconds. My seconds cancel out, and I end up with 6 coulombs are coming out of that battery in 10 seconds. Now, if you remember when we talked about charges, that's a large amount of charge, but that is if we have a net charge of 6 coulomb. Remember, I mentioned that these are all electrically neutral, and take a look at one of the earlier videos in this series where I talk about how charges move through a circuit, there's an equal amount, for the most part, of negative and positive charges, which means this is not a net charge, this is just the total amount of charge that's moving around. So here's how you can find charge going past a point in a given time, and that's a reference back to the looking out the window at the cars. Great. Let's see what else we can do with this, because this is great. We can now get an idea that, oh, we've got different amounts stored in here, and this is the difference between a AAA, a AA, a C-sized, and a D-sized. So let's see what we can find out when it comes to either energy or power. So let's take the 9 volt, for instance. Now, I'm going to play around with units a little bit. We said that we had 9 volts, and that the current is, so let's see, delta V is equal to 9 volts, and our current is equal to 0.6 amps times, say, 1 hour. Let's see, so, and our time would be equal to, say, 1 hour. Let's go ahead and put that in. Now, the reason that I've got this is the following. We mentioned that we could find the power by finding delta V times I, or P equals I delta V, so I can take 9 volts times 0.6 amp, and I have that under these circumstances, a 9 volt putting out 600 milliamps, 9 times 0.6, gives us 5.4 watts. Now, just like we saw in some of the previous stuff, I can now bring the time in where power is equal to energy divided by time, and we end up with, well, if we multiply both sides by time, if I take the power times time, I'll get the energy. So if I multiply this by the 1 hour, because if I have it going at 600 milliamp, the 9 volt battery will last 1 hour, so I multiply it by the time that it will last, and I end up with 5.4 watt hours, which is something that we talked about earlier in the power stuff. So we could then turn this into kilowatt hours, and we could see what the electric company would charge us for it. However, that's not normally how you go about things, because you buy the batteries. But this gives us an idea of how much energy is contained in there. We could turn this into kilowatt hours, though watt hours works just fine. So for the 9 volt battery, the standard one that I have the stats on, we estimate about 5.4 watt hours. Now we could go through some conversions and we could turn that into joules, but for right now I'm just going to leave it like this, and you can convert it into joules as a challenge for yourself. Let's take a look at the AAA. So for instance, our energy, the total energy in that battery, is going to be equal to our power times our time, which is going to be our current times delta V times the time that we can run it for. Well, delta V for a AAA was 1.5 volts, and then we said that the current for this one, if we run it at 1.2 amps, which is 1,200 milliamps, then it will run for 1 hour. We can multiply these out. We've got 1.5 times 1.2 times 1. The content, the energy content of the AAA battery is 1.8 watt hours, noticeably less than the 9 volt. Let's go with the energy content. Oops, not an electric field. Energy content of, let's go to the C-size battery, for instance. So let's do 1.5 volts for our potential difference, our current. It says that we can supply 8 amp for 1 hour, or you could switch that out, 8 milliamp for 1,000 hours. However you want to put that in, these two will multiply to be the same thing, and we get 1.5 times 8 times 1, we get 12 watt hours. So the C-size is actually going to be able to supply more, all things considered, than our standard 9 volt. Let's get an idea of, say, the car battery. That one's going to be interesting. So we've got 12 volts times 50 amp times 1 hour equals 12 times 50, 600 watt hours. And then finally, let's take a look at the iPhone. Okay, so that one was 3.8 volts times, we could go with 1.810 amp times 1 hour. This gives you an idea of the energy content of your cell phone battery if you have an iPhone 6, although many of them are going to be pretty comparable to this, at least a pretty good estimate. That gives us 6.88 watt hours. A bit more than the 9-volt battery, all things considered. Now, this is assuming that the potential difference stays the same. It turns out as you start draining batteries, then their potential difference will actually start to change. So we're using what's called nominal values. But we can find, keeping in mind that current is charge per time, we can multiply by the time to find our current. Pay close attention to units so that you can actually figure out from there. If you wanted to convert this into the energy units that we're more used to, you could convert the watt and the hour. So for instance, let's say that we've got 5.4 watt hours. Well, let's see, a watt is equal to a joule per second. So here's what I'm going to do. I am going to change that out. Instead of the watt, I'm going to say that's 5.4 joules per second times hour. And I'm going to multiply by a special 1. 1 hour is equal to 3,600 seconds. My seconds cancel out, my hours cancel out, and I'm left with joules. So I get 5.4 times 3,600, and I end up with 19,440 joules. That's the energy content, nominally, of a 9-volt battery based on its specs. You could go through and do the same thing with each of these and find out how many joules they end up with. So here's a little bit more you can do with power.